All right, guys. So, with my internet out, I'm going to record what we're going to talk about today. Have you fill out that worksheet as we go. You can notice on my screen I'm not connected to the internet. There's nothing I can do. I checked with Xfinity. Everything's out. We're good to go there. All right. So, comparing functions. It's going to be a kind of combination of our function representation as well as looking at different things. So on that printout, we're going to compare 4 different pizza places. So Domino's Pizza, Papa Ron's, Harry's Pizza, and Pizza Tent, all very famous establishments. I know you guys all know what they are. And we're going to build all the same things, and we're going to see when it would be better to work at certain places. So we see that Papa Ron's has been graphed for us. So that's where our information for Papa Ron's is. Let's start with Domino's just because it's up here in the top left. All right. So Domino's Pizza pays drivers $24 per shift plus $3 per pizza delivered. So the independent variable and the dependent variable have been established within our words here. The independent variable are the pizzas. So the amount of pizzas that get delivered depend, like, we get to control that. We can, go, well, I'm not going to deliver that many pizzas, or I can deliver a bunch of pizzas. While the DV, what depends on the pizzas, is the money that we earn. So this is the money that we end up earning that day. So this $24 per shift is really this constant. So we get $24 plus $3 for every pizza that we end up delivering during the day, which makes sense. So if you were to go into work as a pizza delivery driver and no one orders pizza all day, you would still be expected to get paid something because you got up off the couch, you had to leave your house and go to work. You didn't get to stay at home. So that's where this $24 comes in, and $3 per pizza delivered. So the next thing that I would probably do is build the equation because we have it right here from words. So our equation, f of x, I need to write that smaller because I don't have enough space. F of x, the 3, since it's the independent variable, goes 3x plus 24. So I get $3 for every pizza, and we're going to have $24 right on top of that, regardless of how many pizzas I end up delivering. So if I plug in 0, so f of 0, so 3 times 0 is 0, 0 plus 24. So I don't deliver a single pizza, I'm still going to get paid $24 for that day. Makes sense. I should get paid something even if no one orders pizza that day. It's not my fault that no one has ordered pizza. So then for 3 pizzas, so f of 3, so we get 3 times 3 plus 24. So 3 times 3 is 9, 9 plus 24, $33. So $3 for each pizza plus the 24, I'd make $33 if I just delivered 3 pizzas. Then for 10, 3 times 10 is 30. 30 plus 24 gives us $54 that we'd earn if we delivered 10 pizzas that day. I'm going to take these points right here, and I'm going to plot it on our graph down below. So I have 0, 24, 3, 33, and 10, 54. So we can see right now that working at Domino's starts off better because we get more money from the start, but we quickly start losing more money as we go. So I'm going to draw my line here. Domino's. So now let's convert the rest of these as well. So let's do Papa Ron's next because it's just to the right. So Papa Ron's, all the information given to us is already in the graph. So it looks like we have 0, 18, 3, 30. This looks to be just above 57, so maybe 58, and then 12, 66. So we've got 0, 18, 3, what did I say, 36? 3, 30, and 10, maybe 58. Yeah, I would say 58. So if you kind of look 57, 58, 59, so I'd say 58. And we have our table. Now from our table, I would build the equation. So I have f of x is equal to, so I know what my y-intercept is. It's 18. Now I just need to figure out my rate of change. So my rate of change, let's go from 18 to 30, that's 12. From 0 to 3 is 3, so our rate of change is 12 over 3, or in this case, 4. So once again, our IV is the same. It's the number of pizzas we deliver, and it's our money that we earn overall. To write our word problem, we're going to kind of write it the same way it's written here for Bominos. So this 18 right here is how much we make per shift. So we make $18 just to start, plus $4 a pizza. That's not a pretty bad, that's pretty decent, $4 a pizza. So we make more per pizza, but we start off at a lower rate. So again, if we were just to compare Bominos to Papa Ron's, just these two, Bominos is better when there's less pizza being eaten. So maybe like a Monday or a Tuesday, because people don't really eat pizza on Mondays and Tuesdays. But on those Friday nights where everyone's ordered pizza, you want to work at Papa Ron's because you'd be delivering pizzas like a madman and just making money. So let's look at our next two. Harry's Pizza, if you can guess, Harry's Pizza. We're given the table. We've left one number out. Maybe we can figure out what that is. So again, I would build the equation next. So from 30 to 50, we get 20. From 0 to 10, we get 10. So our rate of change is 20 over 10, or just 2. So 2x, here's our y-intercept, plus 30. Once again, our IV is pizza, DV is still money earned. So at Harry's Pizza, we start with $30 right off the bat. So we show up at work, we basically made $30 for that day. And then we make $2 for a pizza. So every pizza we end up delivering, we get $2. So these are the people you want to like, oh my gosh, that birthday party that just ordered 12 pizzas. That's what I want to deliver and get $2 for each one of those pizzas. All right, got to fill in the blank right here. So let's plug in 3 into our equation. So we plug in 3 into our equation, and we make $36 for delivering 3 pizzas. Let's copy this table onto our graph. So 0, 30, 3, 36, and then at 10 pizzas it was 50, correct? 10 was 50, yes. All right, 10, then 48, so it's right here. just below 51. So right there, line color, line style. So there's Harry's Pizza right there. All right, so let's label it Harry's. So there's Harry's Pizza right there. So Harry's is even better than Domino's on those slow days because you get $30 if no one orders pizza that day. But quickly on those busy days, it's not as good to work at Harry's. All right, last one, Pizza Tent. So Pizza Tent already has the equation written for us. So we're going to, I want this to all be the same color. That's why I'm changing it real fast. So Pizza Tent we're going to do in purple. We already have the equation. So we can use the equation to make the table. We can use the equation to write our words. Order of that doesn't matter. We're going to convert it. So still pizza, still money earned. We could also go and graph this if we wanted to. Let's make the words because that should be the quickest. So a Pizza Tent, we only make $12 a shift. So Pizza Tent is really awful to work on those slow days, I should say. But on those really busy days, we make $5 a pizza. So we start off with $12 for the shift. We haven't delivered a single pizza, but we made $12. I have delivered 3 pizzas. Could have been to one house, doesn't matter. 3 pizzas. That's 15 plus 12. We've already made $27 on 3 pizzas. So on 10 pizzas, F of 10, so we plug it in. That's 50 plus 12, that gives us $62. Way more than everybody else. So let's copy this onto our table. 0, 12. 327. And then 1062. So again, right below the 63, 62. Yes, I purposefully made these graphs look the way they do. And we picked specific points so we can do a bunch of comparisons with it. So that was Pizza Tent. All right. The graph is the best place to do the comparison because everything is visual for it. We can see right off the bat that Pizza Tent, so PT, is better for more pizzas delivered. But Harry's is better for less pizza. So on those days, if you got to pick which place you would work depending on the day, you'd probably pick Harry's on like Monday, Tuesday, Wednesday when not a lot of people order pizza because you'd get $30. But on those days where everyone orders pizza, Friday, Saturday, you'd go Pizza Tent right here. And now we're not worried about, we all know which companies I'm really talking about, and you might be like, well, I'd order from Papa Ron's all the time, so I would never order from Pizza Tent, so why would I? I don't care about that. If all these pizza places had similar quality, based purely on pricing model, you would go work at Pizza Tent for more pizza. You can kind of compare these points right here, and then this point where they all happen to intersect, this point right here, at 6 pizzas, you'd make $42 regardless of where you would work. So 6 pizzas, you'd make $42 regardless of where you worked. And so that's kind of what we do when we compare functions. we get them all into the same frame of reference. So either we get them all into words, we get them all into a table, we get them all into an equation, or we get them all into a graph. So all the similar form, and then we make our comparison. So if we look at the equation, we can see that Pizza Tent has the steeper slope than anybody else, but the lower y-intercept. When we compare a table, we want to make sure we're comparing the same point. So I don't want to have a table where this one's 0, 1, and 2, and everything else is 0, 3, and 10, because this doesn't tell me anything. I need it to be all the same points. All right, the next part on that worksheet was this. I want to compare function A, function B, function C, and function D. I want to order their rate of change from least to greatest, and then their y-intercepts from least to greatest. So function C, we already have that information directly given to us. So m is 3 over 1, b is 0, comma 1. So we're good there. The rest of these, we're going to have to get the information. So let's start with function A. Function A, from 3 to 7 is 4, from 3 to 5 is 2, and we might think something is wrong if we were to look at the next row. 7 to 9 is 2, but 5 to 6 is 1. That's the same ratio, so our slope is 4 over 2, or simplified to 2 over 1, which is what we see. We should be able to use this information right here to fill in the gap. But instead of doing that, I want to build our equation using our build equation techniques. I want to make sure that we still have that in our back pocket. So 2 over 1 is our slope. So we're going to take y1, or not, sorry. Y minus y1 is equal to m x minus x1. I'm going to pick a row in our table. I'm just going to pick this 3 point right here. So we get y minus 3 is equal to 2, parentheses, x minus 3. Again, should have done that in blue because I want all these different problems to be written in the same thing. Okay. So we distribute, so we get y minus 3 is equal to 2x minus 6. Add 3. So y equals 2x minus 3. So here's our equation. So our slope is 2 over 1, or 2. Our y-intercept is negative 3. We could have also done that, built the pattern. We see from here to here is 1, so this had to be 2. From here to here was 2, since this was 1. So this was 2, since this was 1. So this became negative 1, negative 3. We could have also found it using our table, kind of using that pattern against it. All right, so there's our information for A. Let's find our information for B. So the y-intercept is given to us, so we already know what the y-intercept is. Our x-intercept is negative 5. 1, 2, 3, 4, 5. All right. Connect our dots with our line. So we're given a graphical picture on this one. Y-intercept directly given to us, 0, 3. Our slope, start from this dot, get to this dot, we go up 3, right 5, for our slope of 3 over 5. And then function D is in words, so it looks like our IV is minutes, our DV are coins. So we have 4 coins. That's our starting value. Start off with 4 coins, and then we find 3 coins every 4 minutes, so we get 3 over 4x. So our information is 3/4, 0,4 for our y-intercept. So now that we've got them all boiled down to our rate of change and our y-intercepts, we can actually start organizing these from least to greatest. So smallest rate of change is 3/5. Next smallest rate of change is 3/4. Next smallest is 2. And last smallest is function c at 3. Our least y-intercept is -3a. Next smallest is c at 1. Then it's b at 3. And then it's d at 4. So again, we boiled it down to the two most important pieces of information, rate of change and y-intercept, and we compared. The same thing was happening with Bomino's Pizza. We wanted to compare the rate of change, how much money you make per pizza, to how much did you start with. We just needed to make sure we had a similar form to do it. All right, last one. The number of bottles two machines fill are proportional to how many minutes they are operating. Now, last year in 7th grade, you talked about proportional relationships. Proportional relationships have to start at the origin. So proportional relationships have to start at the origin. You can't have a proportional relationship if you don't start at the origin. So technically, all of these graphs are not proportional because they did not start at 0. But because of that, we know that this table automatically gets the point 0, 0. So how many minutes are they operating? Machine A fills 250 bottles every 20 minutes. So let's come up with our IV and our DV for the problem. So we have minutes and bottles. Which one controls the other? Minutes are controlling how many bottles we have. So in our graph, this is minutes, this is bottles. Machine B, I could plot right now, but let's focus more of our attention on machine A. So machine A, we know that at 0 minutes, it's made 0 bottles. Makes sense. You haven't turned on the machine, it hasn't made anything. So our first dot's right here. We also know that, 20 minutes into production, it's able to create 250 bottles. So that gives us our rate of change of 250 over 20, which can be simplified to 25 over 2. And that rate of change is directly what we're going to use. 2 minutes elapse, and our machine is able to make 25 bottles. So now we actually have some points you can plot. So at 4 minutes, we'd have 50 bottles. At 6, we'd have 75, so on and so forth. So let's plot those points. 0 and then 2, 25, 4, 50, and then we can't plot the 250 because it's not on our graph, so we're just going to use that one for the time being. And so machine A has a graph like this. So that's machine A. So we want to know which machine fills faster. So the slope is telling us how we're doing. 25 over 2. So if we were to boil this down to a unit rate, this machine's able to fill 12.5 bottles every minute. The equation is quite simple. It's 25 over 2x. There is no y-intercept, so we don't need to include anything. Machine B, we already have the points, so let's plot it. I'm going to plot it in red. 0, 0, makes sense. Haven't turned on the machine. 340. Then 680. 9, 120. So it's very slight, but we can see in the graphical picture that we're able to, machine B is the better machine. Ever so slightly though, not by much. So graphs are very good for comparing functions because everything's visual. We could find our rate of change. It's 40 over 3. So our equation is 40 over 3x. So if we were to boil this down to its unit rate, 40 over 3 is 16.6 repeating, if I remember correctly. Let me just double check that. It's not 16 point. That's a different problem I was thinking about. It's 13.3 repeating. Knew that didn't sound right in my head. So machine B is able to fill 13.3 bottles every minute. So again, when we compare functions, we need to make sure that we have boiled our functions down to the same form. So either we're going to compare equations, we're going to compare their tables, we're going to compare their graphs. Once you have them in the same form, then you can start making those comparisons. So this is the video I want you guys to watch since my internet is not working today. Yay, love technology. All right, bye guys.